Tonight, we're going to explore why NASA used Mars to reach an asteroid, and why the answer changes how we think about space travel. But before we get there, stay with the dark for a moment. This is what the solar system looks like from the outside, not the tidy diagram with the labeled circles and the colored orbits that you memorized in school, not the illustration with the sun, large and warm at the center, and the planets spaced evenly outward, like rungs on a ladder. This is what it actually looks like from a distance. Black, vast, almost completely empty. The planets, all 8 of them, all the moons and asteroids and comets and dust, occupy less than 1/1,000,000th of the total volume of the solar system. If you shrank the sun to the size of a grapefruit and placed it at the center of a football field, Earth would be a grain of sand somewhere near the 30-yard line. Mars would be another grain of sand, slightly smaller, near the 45. And the asteroid belt, where this spacecraft is headed, would be a thin scattering of dust particles somewhere between the 50-yard line and the far end zone. That is what this mission is crossing. Right now, somewhere in that dark, a spacecraft the size of a van is hurtling through the void at over 12,000 miles per hour. It has been traveling since October 2023. It has covered hundreds of millions of miles already. And on May 15, 2026, something will happen to it that sounds, when you first hear it, like a mistake. It will fly past Mars. Not to visit Mars, not to orbit it, photograph it, sample its soil, or study its weather systems. Not to slow down near it, or establish any kind of relationship with it at all. The spacecraft will approach Mars, pass within 2,800 miles of its surface, closer than the International Space Station is to Earth, and then it will simply keep going. It will not stop. It will not slow down. It will not look back. And when it emerges on the other side of Mars, it will be going somewhere it could not have gone before. That is the thing this video is about. Not just what happened on May 15, 2026, though we will follow that day in detail. Not just the spacecraft and where it is going, though we will follow that too. All the way to a metal world in the asteroid belt that no human instrument has ever seen up close. What this video is really about is the question underneath those questions. Why Mars? Why not just point the spacecraft at the asteroid and go? The answer, when you understand it fully, does not just explain this mission. It changes the way you see the solar system itself. It turns out that the mental model most of us carry for how a spacecraft gets somewhere, the idea of engines and fuel and pointing and pushing, is not wrong exactly, but it is incomplete in a way that matters. The solar system is not a void that spacecraft cross. It is a machine, a vast, ancient, continuously running machine made of gravity and momentum, and the engineers who navigate spacecraft through it have learned over 50 years of hard-won experience to use that machine rather than fight it. When you see it that way, the Mars flyby is not a detour. It is not a workaround for engines that are not powerful enough. It is the mission making use of the most powerful propulsion system available, one that costs no fuel, requires no combustion, and has been running continuously for 4.5 billion years. Mars does not know the spacecraft is coming. Mars will not feel it pass. The red planet will continue its orbit at 54,000 miles per hour, exactly as it has always done, and the spacecraft will borrow a fraction of that momentum so quietly and so cleanly that the planet's path through space will not change by even a measurable amount. That is borrowed gravity, and it is, in the quietest possible way, one of the most elegant things humanity has ever done. Get comfortable. Settle in. There is no need to rush through this. The spacecraft is not rushing. It has been patient for 2.5 years already, and it has 29 more months to go before it reaches its destination. We can afford to take our time tonight. Over the next few hours, we are going to follow this mission from the beginning, from the moment it left Earth on a column of fire in October 2023, through the long quiet of deep space cruise, to the May 2026 flyby of Mars that is happening right now, right around the time you are watching this. And then we are going to follow it forward, into the long dark of the asteroid belt, toward a world made of metal that has been orbiting the Sun since before Earth had an ocean. We are going to understand how gravity becomes propulsion. We are going to understand why a world in the asteroid belt might be the closest thing to Earth's own core that any human instrument will ever touch. And we are going to understand why the answer to this video's title, once you have it, changes something small but permanent in the way you picture the solar system. Not as an empty canvas that spacecraft drive across, but as a machine that already knows how to carry them. Let's start with what you probably already believe about how a spacecraft gets somewhere. You have a destination. You point your engines at it. You burn your fuel and fly there in roughly a straight line, maybe adjusting course along the way. That is how rockets work in the movies. That is how most of us picture it when we see a launch on the news. A rocket goes up, it goes out, it goes somewhere. And for short distances, that picture is basically right. Getting to the moon, you more or less point and go. The journey takes about 3 days. The Apollo missions carried enough fuel to break into lunar orbit, descend to the surface, launch back up, and return to Earth. The distances involved, roughly 239,000 miles at average separation, are small enough that direct travel is practical. Getting to Mars is more complex. You follow a curved path called a Hohmann transfer orbit, an elliptical arc that carries the spacecraft from Earth's orbit out to Mars's orbit. This is timed so that Mars is in the right position when the spacecraft arrives. The journey takes 6 to 9 months, depending on the orbital geometry, but the basic idea still holds. You use your engines to leave Earth. You coast along the transfer orbit. You use your engines again to slow down and enter Mars orbit. The engines are doing the work. The fuel is the resource. But then something changes. Once you get past Mars, once you start talking about the asteroid belt and Jupiter and Saturn and the deep outer solar system, the rules shift in a way that almost nobody outside of aerospace engineering learns about in school. And once you understand it, the way you picture a spacecraft moving through the solar system is never quite the same. Here is the problem, stated plainly. Fuel is heavy, enormously, crushingly heavy, and the relationship between fuel and speed in rocketry is not linear. It is exponential. Every unit of speed you want to add requires not just more fuel, but fuel to carry that fuel, and then fuel to carry the fuel that carries the fuel. This relationship is captured in what engineers call the Tsiolkovsky rocket equation, derived in 1903 by a Russian school teacher named Konstantin Tsiolkovsky, who had never built a rocket and would never see one fly. The equation shows that to double the final velocity of a rocket, you do not double the fuel, you square the fuel requirement. And to reach the speeds needed to cross the outer solar system in any reasonable time frame, the fuel requirements become so large that the spacecraft itself cannot lift off the ground. The math simply does not work. Chemical rockets, the kind that produce the thunderous fire you see at a launch, are extraordinarily powerful but extraordinarily inefficient over long distances. They give you a burst of speed in minutes, and then they are done. Whatever speed you gained in that burn, that is what you have. You coast from there. So how does a spacecraft reach Pluto? How does one reach the edge of interstellar space? How does a machine launched from Earth in 1977 end up beyond the boundary of the solar system today, still transmitting, still going? The answer is not better engines. The answer is borrowed gravity. Think of it this way. Imagine you are standing at the edge of a merry-go-round that is already spinning. You reach out and grab one of the handles as it passes, and for a moment you are pulled along with it. Then you let go. When you release, you are moving faster than you were before. The merry-go-round gave you something. You did not add any energy yourself. You borrowed the energy that was already in the spinning merry-go-round. A gravity assist works on exactly the same principle, scaled up to the mass of a planet moving through space at tens of thousands of miles per hour. But let's make it more precise, because the merry-go-round analogy captures the feel of it without fully capturing the mechanics. Here is what is actually happening. Every planet in the solar system is in motion, not sitting still, moving, always moving. Earth moves at about 67,000 miles per hour in its orbit around the Sun. Mars moves at about 54,000 miles per hour. Jupiter, despite being the largest planet, moves at about 29,000 miles per hour, slower than the inner planets because it has a much larger orbit to complete in each year. Every one of these planets is carrying momentum, an enormous, almost incomprehensible amount of momentum, locked into its motion by the physics of its formation and maintained without loss across billions of years of orbital travel. When a spacecraft approaches a planet, the planet's gravity pulls the spacecraft in. The spacecraft accelerates as it falls toward the planet, gaining speed the way any falling object gains speed. It curves around the planet, following the shape of the gravitational field, and then it releases back into space on the other side. On the way in, it gains speed. On the way out, it carries that speed with it. But here is the part that surprises people. The spacecraft does not just gain the speed it picked up falling toward the planet. That energy, the energy of the fall, is returned on the way out as the spacecraft climbs back away from the planet's gravity. If the geometry is symmetric, the spacecraft arrives and departs at the same speed relative to the planet. The trick is that the geometry does not have to be symmetric relative to the Sun, because the planet is moving. If the spacecraft approaches the planet from behind, falling into the gravity well of a planet that is moving toward it, and curves around in a way that throws it forward in the direction of the planet's motion, the spacecraft emerges from the encounter moving faster relative to the Sun than it entered. It has stolen a tiny fraction of the planet's orbital momentum. The planet, being enormously more massive, loses an amount of energy that is literally immeasurable. But the spacecraft, being tiny, gains something significant. It gains velocity. It gains a new trajectory. It gains the ability to reach a destination that its engines alone could never have made possible. And the planet does not care. Mars is completely unaware that this happened. There is no collision. There is no docking. There is no communication of any kind. A spacecraft the size of a van passed 2,800 miles above its surface, and Mars continued its orbit exactly as it was going to continue it regardless. The gravity assist is invisible to the planet. To the spacecraft, it is everything. This technique has a formal name, a gravity assist, sometimes called a gravitational slingshot, sometimes just to swing by. Mission planners have been using it for more than 50 years, and every major mission to the deep solar system has depended on it. The first spacecraft to use one was Mariner 10 in 1974. Mariner 10 was headed for Mercury, the innermost planet, which sounds like it should be easy to reach. Mercury orbits so close to the Sun that a spacecraft approaching from Earth is moving much too fast relative to Mercury to enter orbit around it without slowing down dramatically. and slowing down requires fuel. Carrying enough fuel to do that was not practical within the mass and budget constraints of the mission, so the mission team used Venus. They sent Mariner 10 on a path that took it past Venus first, using Venus's gravity not to speed up but to slow down and redirect, bending the spacecraft's trajectory into an alignment with Mercury's orbit that would have been impossible to achieve with engines alone. It worked. Mariner 10 became the first spacecraft to visit 2 planets in a single mission. It flew past Mercury 3 times before its attitude control gas ran out, and it did all of it by not going directly to its destination. Then came Pioneer 10, which launched in 1972 and used Jupiter's immense gravity to throw itself out of the solar system entirely. Jupiter is so massive, more than twice the mass of all the other planets in the solar system combined, that a spacecraft flying past it on the right trajectory can gain enough velocity to exceed the Sun's escape velocity altogether. Pioneer 10 was the first human-made object to travel beyond the orbit of all the planets. It did it not by burning more fuel, but by falling past the largest planet in the solar system and letting physics do the rest. But the mission that defines what borrowed gravity is capable of, the one that still stands as the most audacious use of planetary mechanics in the history of spaceflight, is Voyager. In 1977, NASA launched 2 spacecraft called Voyager 1 and Voyager 2. The mission was possible because of a rare alignment of the outer planets that occurs once every 176 years. Jupiter, Saturn, Uranus, and Neptune were positioned in a configuration that allowed a spacecraft to use each planet's gravity in sequence, swinging from one to the next like a stone skipped across water. Each encounter adding velocity and reshaping the trajectory for the next one. Voyager 2 used Jupiter to reach Saturn, Saturn to reach Uranus, Uranus to reach Neptune. Each flyby accelerated it. Each flyby redirected it. Each flyby sent it somewhere its engines could never have sent it alone. Without those gravity assists, reaching Neptune would have required a journey of 30 years. With them, Voyager 2 arrived in 12. Today, both Voyager spacecraft are in interstellar space. Voyager 1 crossed the heliopause, the boundary between the solar wind and interstellar medium, in 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018. They are the farthest human-made objects in history, traveling at speeds that no chemical rocket could have given them, carrying instruments that are still transmitting data from beyond the edge of the solar system. They got there because engineers in the 1970s understood the geometry of the solar system precisely enough to use its momentum as free fuel. The missions that followed learned from Voyager and refined the technique. Galileo, launched in 1989 and destined for Jupiter, was too heavy to fly a direct trajectory. Instead, NASA sent it on a path that used Venus once and Earth twice, 3 separate gravity assists across 6 years before the spacecraft had accumulated enough velocity to reach Jupiter. Engineers called it the Vega trajectory, Venus-Earth-Earth gravity assist. It was elegant in the way that all good engineering is elegant, doing more with less, using what was already there rather than carrying what was not. The Galileo mission spent 8 years in the Jovian system after arrival, discovering evidence of a subsurface ocean beneath Europa's icy crust, detecting volcanic eruptions on Io so energetic they dwarfed anything on Earth, and returning data that fundamentally changed what scientists understood about the outer solar system. None of it would have been possible without the 3 gravity assists that got it there. Cassini, launched in 1997 and destined for Saturn, used a similar strategy. 4 gravity assists in total, Venus twice, then Earth, then Jupiter, building up speed across nearly 7 years of cruise before it arrived at Saturn in 2004. The Saturn orbit insertion burn, the engine firing that slowed the spacecraft enough to be captured by Saturn's gravity, was one of the most tense moments in mission history. The spacecraft had to pass through a gap in Saturn's rings, fire its engine behind the planet, where communication with Earth was impossible, and emerge on the other side either in orbit or lost. It emerged in orbit. Cassini spent 13 years at Saturn. It discovered geysers of water vapor erupting from the south pole of Enceladus, a small moon that turned out to have a warm subsurface ocean in contact with a rocky core, conditions that some scientists believe could support life. It descended a probe called Huygens into the atmosphere of Titan, Saturn's largest moon, and returned images of a world with rivers and lakes and rain, all made not of water but of liquid methane. It mapped Saturn's rings in detail no previous mission had approached, all of it powered, in the beginning, by borrowed gravity from 4 planets it visited along the way. New Horizons, launched in 2006 and aimed at Pluto, used Jupiter to cut 14 months off its journey. Without that assist, New Horizons would have arrived at Pluto in 2016. With it, the spacecraft arrived in July 2015, and the images it sent back revealed something nobody expected. Not the dead, cratered, featureless world that most scientists had predicted, but a geologically active place with mountain ranges of water ice, a vast plain of nitrogen ice the shape of a heart, blue atmospheric haze layers, and a surface that appeared to be renewed by processes that are still not fully understood. A single gravity assist shortened the journey by over a year, which meant the images came back a year earlier, which meant scientists have had a year more of Pluto data than they would have had otherwise. In deep space exploration, time is everything. Every year of additional data matters enormously, and borrowed gravity buys time. There is one more mission worth mentioning here, because it is directly relevant to what Psyche is trying to do. The Dawn spacecraft, launched in 2007, was the first mission ever to orbit 2 different bodies in the asteroid belt. It visited the asteroid Vesta in 2011, spent 14 months mapping the asteroid's surface, studying its geology, measuring its composition and gravitational field. Then it left Vesta's orbit and traveled to the dwarf planet Ceres, arriving in 2015 and discovering bright white spots on the floor of a crater called a crater that turned out to be deposits of sodium carbonate, salt pushed to the surface by briny water from a subsurface reservoir. This was evidence that Ceres, despite being in the asteroid belt, has liquid water beneath its surface. Dawn did this using ion propulsion, the same technology the Psyche spacecraft uses, the same patient blue glow of accelerated xenon ions building velocity across years rather than minutes. Psyche is Dawn's direct descendant in terms of propulsion philosophy. Patient, efficient, willing to trade raw speed for the ability to maneuver when it matters. But Psyche needs to get to the asteroid belt faster than Dawn got to Vesta, and it needs to arrive with the correct trajectory for orbital insertion around a specific target. The ion thrusters alone cannot achieve that on the required timeline. The geometry demands more velocity in a different direction than years of patient xenon acceleration can provide. And so the mission does what every deep space mission does when the math demands it. It borrows from Mars. The Psyche spacecraft launched on October 13, 2023 from Kennedy Space Center in Florida, carried into orbit by a SpaceX Falcon Heavy rocket. From the moment it left Earth, the mission had one ultimate destination: Asteroid 16 Psyche, a metal world orbiting the Sun between Mars and Jupiter. Its 4 xenon ion Hall effect thrusters produce approximately 250 millinewtons of force each. To understand how small that is, think about a standard AA battery, the kind you put in a television remote. When you drop one on a table from a few inches up, the force of the impact is roughly equal to the force these thrusters produce. That is what is pushing a spacecraft toward the asteroid belt, which sounds impossible, and it would be if the thrusters ran for a few minutes, the way chemical rockets do, but they do not run for a few minutes. They run for months, for years, almost without interruption, adding a tiny increment of velocity every second, accumulating it across the vast timescales of deep space transit until the tiny force has built into something significant. Even so, the geometry of the trajectory to Psyche requires more than the ion thrusters alone can produce on schedule. The spacecraft needs to arrive in July 2029. To get there in time, with the right trajectory and the right velocity for orbital insertion, the mission needs additional acceleration in a specific direction. Mars is in that direction. Mars is moving at 54,000 miles per hour, and Mars in May 2026 is in exactly the right position to provide what the spacecraft needs. On May 15, 2026, at a speed of 12,333 miles per hour, the Psyche spacecraft will pass 2,800 miles above the surface of Mars. It will not slow down. It will not stop. It will not even pause to look. It will fall toward Mars, curve around it, and emerge on the other side going somewhere it could not have gone before, carrying momentum borrowed from a planet that will never know it passed. 2 days after that flyby, the mission enters Cruise 2, the long dark, 29 months to the asteroid belt, with the thrusters firing almost without pause, building on the speed Mars gave them, carrying a spacecraft made by human hands toward a world made of iron. But before we follow the spacecraft into the dark, there is something worth understanding about what it did during those flyby hours. Because the mission team did not send Psyche past Mars just for the gravity assist. They sent it past Mars because they are not the kind of engineers who leave hardware idle when there is something to be learned. And Mars, it turns out, was a very good teacher. On May 3, 2026, 12 days before the closest approach, the Psyche spacecraft pointed its cameras toward Mars for the first time. It was 3 million miles away. From that distance, Mars looked small, a pale reddish circle, sharp-edged, surrounded by absolute darkness. Not the imposing presence you might imagine for the largest gravitational anchor in the inner solar system. It was not the rusty, canyon-scarred world you have seen in high-resolution orbital photography. Just a disk of light, cold and quiet, holding its orbit with the same indifference it has held for 4 billion years. It is, in the most literal sense, a pixel, or close to one, and that matters more than you might think. The Psyche mission launched in October 2023. From the moment it left Earth, it was alone in the dark, not the companionable dark of low Earth orbit, where the planet fills half the sky and you are never more than a few hundred miles from the surface. The deep dark. The dark of interplanetary space, where the sun is a brilliant point of light rather than a warm presence, where temperature swings between direct sunlight and shadow, can span hundreds of degrees in seconds, and where the nearest large object is always millions of miles away. For 2.5 years, every object the spacecraft's cameras could point at appeared as exactly that. A point, a pixel, a cluster of pixels at best. The moon from deep space is a tiny bright dot. Earth, from hundreds of millions of miles away, is a mote of light, Mars, for most of the crews, was the same. This creates a real problem for mission engineers, and it is a problem that most people who follow space missions never think about. Spacecraft instruments are tools. Like all tools, they require calibration. A thermometer needs to be checked against a known temperature before you trust it to measure an unknown one. A scale needs to be zeroed before you weigh something. A spectrometer, which measures the wavelengths of light reflected from a surface, needs to be checked against a target whose spectral properties are precisely known before you trust it to characterize the spectral properties of something that has never been measured before. Before launch, every instrument on the Psyche spacecraft was tested and calibrated extensively. Teams of engineers spent months in laboratory settings pointing the imager at targets of known reflectivity, running the magnetometer through known magnetic fields, exposing the gamma-ray spectrometer to known radiation sources. They built calibration curves. They characterized the instrument's responses. They documented everything. And then the spacecraft launched, and the instruments were exposed to the actual environment of deep space for the first time. Deep space is not a laboratory. The thermal environment is far more extreme than any vacuum chamber can simulate. The radiation environment, cosmic rays streaming in from all directions and from the sun, is different from anything reproducible on the ground. Materials behave differently. Detector responses drift. An instrument that was perfectly characterized before launch is not necessarily the same instrument 2.5 years later. The only reliable way to check is to point the instruments at something you already know. Something with independently verified properties measured by other instruments on other spacecraft, published in peer-reviewed literature, agreed upon by the scientific community. A calibration target you can trust. For the Psyche mission in May 2026, that target was Mars. Sarah Bairstow is the mission planning lead at NASA's Jet Propulsion Laboratory in Pasadena, California. Her job, broadly stated, is to make sure the spacecraft does the right thing at the right time, every time, for the entire duration of the mission. In practice, that means translating the science team's objectives into specific commands, specific instrument pointings, specific thruster firings, specific communication windows, and loading all of that into the flight computer before the spacecraft needs to execute it, because the spacecraft cannot be commanded in real time from Earth. This is something worth pausing on, because it is easy to forget when you watch mission footage of teams in control rooms watching telemetry screens. The Psyche spacecraft, during the May 2026 flyby, was approximately 280 million miles from Earth. A radio signal traveling at the speed of light takes about 25 minutes to make that journey one way. A round trip, a command sent, and an acknowledgement received takes roughly 50 minutes. If something unexpected happened during the flyby, and the team on the ground noticed it immediately and sent a response command, that command would arrive 25 minutes after it was sent. By then, the flyby would be over. The spacecraft would already be on the other side of Mars, so Bairstow and her team do not command the spacecraft in real time during critical events. They pre-program it. They load every action, every decision tree, every contingency response into the flight computer before the event begins, and then they let the spacecraft execute autonomously. The team on the ground watches the telemetry, but they are watching history. What they see on their screens happened 25 minutes ago. We are now exactly on target for the flyby, Bairstow said in early May 2026, and we've programmed the flight computer with everything that the spacecraft will do throughout May. Everything. Every camera pointing, every instrument activation, every calibration sequence, every observation window, every thruster adjustment. All of it decided in advance, all of it loaded and verified, all of it ready to execute without any further input from the team on the ground. That level of pre-planning is extraordinary, even by the standards of deep space mission operations, and it reflects something important about what the team was trying to accomplish during the flyby. They were not just passing Mars, they were running a comprehensive science campaign against one of the most studied objects in the solar system. The approach geometry deserves its own moment, because it is quietly beautiful in the way that orbital mechanics tends to be when you slow down and look at it carefully. The spacecraft does not approach Mars from the sunlit side. It comes in from the night side, the dark hemisphere, the half of the planet turned away from the sun, where the surface is in shadow and the atmosphere above the terminator, the boundary between day and night, is catching only the oblique light of a distant star. On approach, seen from the spacecraft, Mars does not look like the full red disk you might expect. It looks like a crescent. It looks like a thin, curved sliver of illuminated atmosphere at the edge of an otherwise dark circle. The rest of the planet invisible against the surrounding black of space. Think of how the moon looks a few days after the new moon. That fragile, curved line of light in a dark sky, delicate and easy to miss if you are not looking for it. Mars, from the approach trajectory, looks the same way. A crescent barely there. Just enough light to confirm the planet exists. That crescent light is scientifically useful in a specific way. The light coming from the crescent is not direct sunlight reflected off the Martian surface. It is sunlight that has passed through the Martian atmosphere, through the thin veil of carbon dioxide and suspended dust that wraps the planet. As light travels through that atmosphere, it is absorbed and scattered and changed in ways that are characteristic of the atmospheric composition. The dust, fine iron oxide particles and silicate grains suspended at various altitudes scatters certain wavelengths more than others. The result is a spectral signature, a fingerprint in the light that tells scientists something about what the atmosphere is made of and how the dust is distributed. By measuring this scattered atmospheric light with the multispectral imager, the calibration team gets information about how the instrument responds to light that has been processed by a planetary atmosphere. This is information that matters because when the spacecraft arrives at asteroid Psyche in 2029, the light it measures will also have interacted with whatever is on the asteroid surface, and understanding how to interpret processed light rather than raw reflected sunlight is part of making the science work correctly. Then the spacecraft passes the closest approach point, 2,800 miles above the surface, moving at 12,133 miles per hour. This is the moment of maximum gravitational interaction, the deepest point of the arc, the instant when Mars is pulling hardest and the spacecraft is being bent most dramatically onto its new trajectory. And as it emerges on the other side of the planet, the view through the imager shifts entirely. Mars goes from a crescent to a nearly full illuminated disk. The geometry is flipped. Now the spacecraft is on the sunlit side, looking back at a Mars that is almost fully lit, the rusty surface visible, the polar ice caps faintly distinguishable, the Great Valles Marineris canyon system, a dark scar running roughly along the equator, 2,500 miles long, and in places 4 miles deep, the longest and deepest canyon system in the solar system. Two completely different views of the same planet within a few hours of each other. Crescent on approach, nearly full on departure. Two different lighting geometries, two different atmospheric path lengths for the light to travel, two different calibration opportunities from a single pass. That is not an accident. The mission team designed the flyby trajectory to capture both. When you are sending a spacecraft 2.2 billion miles to study something no instrument has ever seen, you do not waste a single hour of data collection time. Now here is why all of that calibration matters at the destination. When the Psyche spacecraft arrives at Asteroid 16 Psyche in July 2029, it will be the first instrument ever to observe that world from close range. There is no prior data from orbital observation. There are no other spacecraft there to cross-check against. There are no peer-reviewed papers describing what the surface looks like in infrared, or what the magnetic field configuration is, or what the gamma-ray emission signature is. Everything the instruments measure will be new. Everything will be the first measurement of its kind. There is no independent reference to compare against. Which means, if an instrument is miscalibrated, if it is reading 10% high or responding slightly differently to blue wavelengths than it did before launch, the scientists will not know. They will receive a number, they will publish a composition estimate, and that estimate will be wrong by whatever amount the miscalibration introduced. Not wrong in a way that is obvious. Wrong in a way that is subtle and potentially undetectable without a calibration reference. Mars is the calibration reference. Mars has been studied by spacecraft in orbit since Mariner 4 flew past it in 1965. There are currently multiple active orbiters around Mars, including the Mars Reconnaissance Orbiter, the Mars Atmosphere and Volatile Evolution Mission known as MAVEN, and the European Space Agency's Mars Express. There are rovers on the surface. There are decades of published spectral data on how the Martian surface and atmosphere reflect and absorb light at every wavelength the Psyche imager uses. If the Psyche imager looks at Mars and returns a number that matches what every other instrument in the history of Mars science has returned, the calibration is good. If it returns a number that is slightly off, the team knows by exactly how much, and they can correct for it before they start making measurements at the asteroid. The magnetometer performed a similar check during the flyby. Mars has a complex magnetic environment. It has no global magnetic field of its own, its core having cooled and solidified long ago, but it has regions of crustal magnetism, ancient remnant fields locked into rock that solidified when Mars had an active dynamo. It also has an induced magnetosphere, a temporary magnetic structure created when the solar wind interacts with the planet's ionosphere. All of this has been measured extensively by previous spacecraft, particularly MAVEN, which has been studying Mars's magnetic environment since 2014. The Psyche magnetometer, during the flyby, measured the same environment and compared its readings against the established MAVEN dataset. Any discrepancy would reveal a calibration offset that the team could then account for when interpreting the magnetometer data at the asteroid. The gamma ray and neutron spectrometer measured how the cosmic ray and particle radiation environment changes during a planetary encounter, collecting data that will help the team interpret the background radiation levels at the asteroid, which affect how the spectrometer reads the elemental composition of the surface. Every instrument powered, every instrument watching, every instrument building a calibration baseline that will make the science at the asteroid more reliable. But there was one more thing the team was doing during those flyby hours. Something that sounds at first like it belongs to a completely different mission. They were looking for moons, not the known moons of Mars. Phobos and Deimos are well documented, their orbits precisely known, their positions during the flyby fully accounted for. The cameras were not looking for Phobos. They were looking for things that might not yet be in any catalogue. The space around planets is not always as empty as it appears. Mars is surrounded by a tenuous cloud of dust, micron-sized particles liberated from the surfaces of Phobos and Deimos by micrometeorite impacts, slowly spreading into a diffuse ring along the orbital plane of the moons. There may also be very small, very faint co-orbital objects, tiny bodies sharing Mars's orbital path that have never been detected from Earth because they are simply too small and too dark to see at this distance. During the flyby, Psyche's cameras scanned the surrounding space systematically, imaging regions at various distances from the planet, looking for any point of light that moved against the star background in a way that indicated it was orbiting Mars rather than orbiting the Sun. Nothing significant was found, but the finding, or rather the absence of finding, is itself data. It confirms the region around Mars is as clean as the models predict, which is a baseline check on the models themselves. More importantly, the search was practice, because when the spacecraft arrives at Asteroid Psyche in 2029, the very first thing the science team will need to do before attempting orbital insertion is exactly the same search. They will need to know whether the asteroid has any natural satellites, any co-orbiting debris, any material that could pose a navigation hazard to a spacecraft trying to spiral into a close orbit around a metal asteroid in the middle of the belt. That search, in 2029, will use the same cameras, the same observation sequences, the same analysis software, the same decision protocols that the team rehearsed during the Mars flyby. If something unexpected is found near the asteroid, the team will already know how to respond, because they will have run the same scenario before. This is what good mission design looks like at its most careful. Not just getting the spacecraft to the destination, rehearsing every critical operation before it matters, using every opportunity in transit to reduce the number of unknowns that will face the team when the moment of truth arrives. Sarah Bairstow described the calibration opportunity in terms that cut through all the technical complexity to the essential point. This is our first opportunity in flight to calibrate Psyche's imager with something bigger than a few pixels. Something bigger than a few pixels. That is the operational context in 2 sentences. For 2.5 years, every target the imager could point at was so far away, so reduced by distance, that it appeared as essentially nothing. A smear of light, a cluster of 3 or 4 pixels at best. Mars, for the first time, was a full disk, a real object. It was something with known properties and known measurements, against which the instrument could be properly characterized rather than just staring into the dark and hoping the calibration held from before launch. And then, as suddenly as it began, the flyby was over. At 12,333 miles per hour, the closest approach window lasted only a few minutes. The planet grew in the cameras, reached its maximum apparent size, and then began to shrink. The crescent reformed on the far side, a mirror image of what the cameras had seen on the approach. The magnetic field readings settled as the spacecraft moved away from the induced magnetosphere. The gamma-ray environment returned to deep space baseline. The gravity assist was complete. The spacecraft emerged from the encounter, carrying borrowed momentum it could not have built with engines alone. Its trajectory had changed. The plane of its orbit had shifted, tilted toward the asteroid belt in a way that would have required years of ion thruster operation to achieve independently. The velocity was higher. The destination was closer in terms of the trajectory geometry than it had been before the flyby, and Mars continued its orbit, completely unaware. 2 days later, on May 17, 2026, Cruise 2 began. The spacecraft turned its solar arrays back toward the Sun, oriented its thrusters toward the asteroid belt, and resumed pushing. Not loudly, not with fire. with the same quiet blue glow of ionized xenon that has been its constant companion since launch, building velocity with infinite patience across a journey that will not end until July 2029. But before we follow the spacecraft into that long dark, there is a question we have been quietly carrying since the opening minutes of this video. We know how the spacecraft is getting to the asteroid. We have followed the gravity assist, the instruments, the calibration, the rehearsals. We understand the propulsion. We understand the patience required. What we have not yet asked, at least not fully, is the oldest question. Why? Why does this asteroid specifically justify 29 more months of cruise on top of 2.5 years already spent in transit? What is waiting at the end of 2.2 billion miles that cannot be learned any other way? What is asteroid Psyche? It was discovered on the 17th of March 1852 by an Italian astronomer named Annibale de Gasperi. He was working from the Astronomical Observatory of Capodimonte in Naples, a hilltop facility overlooking the city and the bay beyond, scanning the sky with the methodical patience that characterized most astronomical work of that era. No cameras, no computers, just a telescope, a trained eye, and the accumulated knowledge of a man who had spent years learning to distinguish between a star that belonged in its position and a point of light that did not quite behave the way a star should. De Gasperis was good at this. He discovered 9 asteroids in total over the course of his career, a remarkable number for the time, each one found by the same patient method. Look carefully, compare tonight's sky against last night's sky, notice what moved. On that March night in 1852, something moved. He designated it 16 Psyche, the 16th asteroid ever catalogued by humanity. He noted its position, estimated its brightness relative to the surrounding stars, recorded it in the official catalogue, and moved on to the next patch of sky. That was 174 years ago. For the century and a half that followed, Psyche was observed and re-observed, catalogued and recategorized. Every improvement in telescope technology brought new observations. Every new technique in astronomical analysis was eventually applied to it. Photographic plates replaced the naked eye. Spectroscopy allowed scientists to analyze the composition of light reflected from its surface. Radar gave a new way to probe its shape and density. Thermal infrared measurements revealed how its surface absorbed and radiated heat, and the more scientists looked at Psyche, the more it refused to fit any of the existing categories. There is a classification system for asteroids. It is built around composition and reflectivity, the way an asteroid's surface reflects light at different wavelengths. Most asteroids fall into one of a handful of broad categories. The most common type, accounting for the majority of asteroids in the inner belt, are called S-type asteroids. S for silicaceous. They are rocky, made primarily of silicate minerals, the same basic material that forms the rocky mantles and crusts of the inner planets. The near-Earth asteroid Eros, visited by the Near-Shoemaker spacecraft in 2000, is an S-type. It looks, in close-up images, like a lumpy potato made of reddish-grey rock. The second major category is C-type. C for carbonaceous. These are darker asteroids, less reflective than the S-types, rich in carbon-bearing compounds and organic material. They are relics of the outer solar system, material that formed in the cold regions beyond the frost line where volatile compounds survived. The asteroid Bennu, visited by the OSIRIS-REx mission and sampled in 2020, is a C-type. It returned samples to Earth in 2023 that contained amino acids and other organic molecules, building blocks of the chemistry that eventually, somewhere, became life. Psyche is classified as M-type. M for metallic, and that classification alone is remarkable because M-type asteroids are rare. They make up only a small fraction of the total asteroid population. Most material in the solar system is rock or ice. Metal, in the quantities that Psyche appears to represent, does not form on its own in significant amounts at the asteroid belt's distance from the Sun. Metal ends up concentrated in places like Psyche through a specific process, one that requires conditions that only existed in the first few million years of the solar system's history. Psyche's radar albedo is high. Radio waves bounce off it energetically, the way they bounce off metal rather than rock. Psyche's density is high, somewhere between 3,400 and 4,100 kilograms per cubic meter, depending on the analysis method, falling between the density of rock and the density of pure iron. Psyche's thermal inertia is high, consistent with a surface that heats and cools the way metal does rather than rock. Every measurement points in the same direction, not all the way to pure iron, but further toward metal than anything else in the belt. Psyche does not fit the categories because Psyche is not like anything humanity has yet visited up close. It is, in all likelihood, something genuinely different, something that formed under conditions that do not exist in the solar system today and have not existed for 4.5 billion years. To understand what Psyche might be, you have to go back to the beginning, not the beginning of the solar system as a settled place with planets and orbits and the familiar architecture we observe today. The beginning as a catastrophic, violent, still-forming system where the rules were being written in real time by the physics of gravity and heat and collision. About 4.6 billion years ago, a cloud of gas and dust began to collapse under its own gravity. Most of the material fell toward the center, forming the Sun. A fraction remained in a rotating disk around the young star, and that disk was the raw material from which everything else in the solar system eventually formed. Close to the Sun, where temperatures were high, only materials with high melting points could condense from the gas phase into solid particles. Metals, primarily iron and nickel. Silicate minerals. Further from the Sun, beyond what astronomers call the frost line, temperatures were low enough for volatiles to freeze. The outer disk was rich in water ice and other icy compounds. In the inner disk, the solid particles began to stick together. Dust grains collided and adhered. Small clumps formed, small clumps collided and grew into larger clumps. This process, called accretion, eventually produced bodies large enough to have significant gravity of their own. These bodies were a few tens to a few hundreds of miles across. These are the planetesimals, the building blocks of the planets. Some planetesimals were large enough that their interiors became warm. The warmth came from two sources: the heat generated by the ongoing collisions that built them up, and the heat from the decay of short-lived radioactive isotopes that were abundant in the early solar system, particularly aluminum-26, which has a half-life of only 717,000 years. That radioactive heat was significant. In large enough planetesimals, it was enough to melt the interior, and when rock melts, the different materials within it separate by density. This process is called differentiation, and it is the same process that built the layered interior structure of every rocky planet in the inner solar system, including Earth. Iron and nickel, being dense, sank toward the center of the melting planetesimal. Silicate minerals, being less dense, rose toward the surface. The result was a planetesimal with a layered structure, an iron-nickel core at the center, a rocky mantle of silicate minerals surrounding it, a thin rocky crust at the surface, a miniature planet in all the ways that matter. And then the bombardment continued, In the early, chaotic asteroid belt, planetesimals collided with each other at velocities and angles that spanned a wide range of outcomes. Some collisions were low-velocity mergers, some were catastrophic disruptions, but some, happening at intermediate velocities and at specific approach angles, did something different. They hit the target body hard enough to strip material from its surface without shattering the whole body. A glancing blow, delivered with enough energy, could excavate the outer layers of a differentiated planetesimal, peeling away the rocky crust and mantle without destroying the iron core below. And if that happened repeatedly, over millions of years of ongoing bombardment, a differentiated planetesimal could be gradually stripped of its outer layers, one collision at a time, until what remained was not a complete layered body. What remained was the core, just the iron and nickel heart of a world that began forming but never finished, the inside of something, now on the outside, exposed to space for the first time since it formed 4.5 billion years ago, in the heat of a young solar system that no longer exists. Scientists believe asteroid Psyche may be exactly that. The hypothesis is called the core remnant theory, and it is the leading scientific explanation for why Psyche has the physical properties it has. It is the explanation that best fits the density measurements, the radar albedo, the thermal properties, and the spectroscopic data. It is the explanation that the mission was designed to test. But it must be said clearly, it is a hypothesis, not a confirmed fact. The data collected from Earth and Earth-orbiting telescopes is consistent with Psyche being a metallic core remnant. It does not prove it. There are alternative hypotheses that the data cannot yet rule out. One alternative is that Psyche is a primitive metallic asteroid, an object that formed directly from metal-rich material in the early solar system, without ever differentiating. Another is that Psyche is a partially differentiated body, large enough to have begun differentiation, but not large enough to complete it. A third is that Psyche is a core remnant, substantially modified by later impacts, with silicate material from impactors mixed into the metallic surface. These are not fringe ideas. They are legitimate scientific positions held by serious researchers. The mission exists precisely because ground-based observations cannot distinguish between them. Only close-range observations from orbit can resolve the question. What Psyche almost certainly is not, is a typical rocky asteroid. The measurements are too consistent across too many different techniques for the metallic character to be a measurement error. Something unusual is going on with this object. The mission will tell us what. What would it actually be like to stand on Psyche? Psyche's dimensions have been estimated from Earth-based radar and infrared observations. It is roughly 173 miles long along its longest axis. Its surface area is approximately 64,000 square miles, roughly comparable to the state of Florida. It rotates on its axis approximately once every 4 hours and 12 minutes, meaning days and nights on Psyche would last about 2 Earth hours each. The surface gravity is extraordinarily weak. At Psyche's surface, the gravitational acceleration would be approximately 0.6% of Earth's. A person weighing 180 pounds on Earth would weigh about 1 pound on Psyche. Lifting a car would require about the same effort as lifting a large dog on Earth. Dropping an object from shoulder height would take approximately 25 seconds for it to reach the ground. Not because it is falling through something resistant, but because the gravity pulling it down is so weak that it accelerates almost imperceptibly. Walking would not work the way it works on Earth. Each footstep would send you floating upward and forward. Running would be genuinely dangerous, a running stride generating enough upward force to launch you 30 or 40 feet into the air, where you would drift for a minute or more, before slowly settling back down, potentially hundreds of yards from where you started. Escape velocity from Psyche's surface is only about 180 miles per hour, and the surface itself, no one knows what it looks like at the scale of a few feet. Is it smooth, ground down by 4.5 billion years of micrometeorite bombardment? Is it jagged and crystalline, the internal structure of an iron-nickel body exposed at the surface? Is it covered in fine metallic dust? The surface of an iron-nickel world, exposed to the vacuum of space for 4.5 billion years, has no analogue in human experience. The closest analogues are iron meteorites, pieces of ancient metal that have survived the journey through Earth's atmosphere. Scientists have studied them extensively. They have an internal crystal structure called the Wittmann-Steffen pattern, long parallel bands of different iron-nickel alloys that only forms during extremely slow cooling over millions of years, the kind of cooling that happens deep inside a planetary body. If Psyche's surface exposes material like iron meteorites, which the core remnant hypothesis would predict, the spacecraft's cameras in 2029 might be looking at something that resembles those meteorite interiors, scaled up to a world 173 miles long. That is what is waiting at the end of 2.2 billion miles, something no human instrument has ever seen. This is something that might be the exposed heart of a dead world, stripped of everything that once surrounded it, silent and ancient and patient in the dark between Mars and Jupiter. And its existence, if the core remnant hypothesis is correct, connects to something much closer, something that has been with every human being who has ever lived, every night of their life just below their feet. That connection is the next part of this story. Lindy Elkins-Tanton grew up in a family that moved often. Her father was a geologist, and geologists go where the rock is. She spent parts of her childhood in different states, in different landscapes, in different geological settings, and somewhere in that peripatetic upbringing she absorbed something that stayed with her. It was an understanding that the ground beneath your feet is not just dirt. It is a record, a compressed, layered, ancient record of processes that operated before any human being existed, before any life existed, going all the way back to the formation of the planet itself. She earned her undergraduate degree, then her doctorate, then spent years as a researcher and faculty member at MIT, and then Arizona State University, where she eventually became the founding director of the School of Earth and Space Exploration. Along the way, her research focused on a question that sits at the intersection of geology and planetary science, and the deep history of the solar system. How do rocky planets build their interiors? It is a question that sounds straightforward until you try to answer it. You can study the surface of a rocky planet. Spacecraft can photograph it. Rovers can sample it. Seismometers can listen to it. You can study the atmosphere, the magnetic field, the radiation environment. You can study a planet from the outside in remarkable detail. But the interior is another matter. The interior of a rocky planet is separated from the surface by tens to hundreds of miles of crust, and then thousands of miles of mantle. All of it at temperatures and pressures that no instrument currently in existence could survive for more than moments. The deepest borehole ever drilled into Earth's surface is the Kola Super Deep Borehole in Russia, begun in 1970, and drilling continuously for 24 years. It reached a depth of 7.6 miles, into a planet whose radius is nearly 4,000 miles. The Kola borehole penetrated less than 0.2% of the distance to Earth's center. It never came close to the mantle, let alone the core. And even at that modest depth, the temperatures and pressures were so extreme that the drill bits degraded rapidly and the project had to be abandoned when the rock became too hot and too plastic to drill further. The core of the Earth begins approximately 1,800 miles below the surface. It is divided into two regions. The outer core, extending from about 1,800 miles to about 3,200 miles depth, is liquid. Liquid iron and nickel, with smaller amounts of lighter elements, sulfur and oxygen and possibly hydrogen, in continuous convective motion. That convection, iron-rich liquid churning in slow currents, driven by the temperature difference between the hot inner core and the cooler mantle above, is what generates Earth's magnetic field, the dynamo that protects the planet. The inner core, from about 3,200 miles to the center at 3,958 miles, is solid. Solid iron and nickel, at temperatures estimated between 9,000 and 13,000 degrees Fahrenheit, comparable to the surface of the Sun, but kept solid despite those temperatures by the immense pressure of everything above it. We know all of this not from direct observation, but from seismic waves. When an earthquake occurs, it sends energy waves outward in all directions through the Earth's interior. There are different types of waves: compressional P waves that can travel through both solid and liquid, and shear S waves that can only travel through solid material. Both types travel at speeds determined by the density and rigidity of the material they pass through. When they encounter a boundary between materials of different properties, they change speed and direction. By placing seismometers around the globe and recording the arrival times and patterns of waves from earthquakes, scientists can work backward from the data to infer the structure the waves pass through. The absence of S waves in certain regions reveals the presence of liquid material in the outer core. The slight increase in P wave velocity in the very center reveals the solid inner core. It is an extraordinary scientific achievement, using the tremors of earthquakes to X-ray the planet from the inside. But it is indirect, always indirect. The seismic waves tell us the density of the material they pass through. What they cannot tell us is the precise chemical composition, the crystal structure, the detailed behavior of iron and nickel at core conditions, or the exact temperature profile from the surface to the center. For those answers, scientists rely on laboratory experiments, compressing iron and iron-nickel alloys in devices called diamond anvil cells to the pressures found in planetary cores, measuring how the material behaves, and extrapolating the results to conditions more extreme than any laboratory can achieve. The models are good. They are remarkable, actually, given the constraints. But they are models. They are not measurements. There has never been a measurement of Earth's core. Not a direct one. Not a sample. Not a photograph. Not a temperature reading taken from within the core itself. The center of our own planet is, in a very real sense, the most inaccessible place in the solar system. Lindy Elkins-Tanton looked at that problem, the fundamental inaccessibility of planetary cores, and looked at asteroid Psyche and saw something. If Psyche is what the data suggests, if it really is the exposed iron-nickel core of a differentiated planetesimal, then Psyche is made of the same material that makes up the cores of the inner rocky planets, not identical in every detail, not Earth's core specifically, but the same basic material, formed through the same basic process, shaped by the same physics of differentiation and planetary formation that built every rocky planet in the inner solar system. Orbiting Psyche for 20 months, mapping its surface composition with the spectrometers, measuring its magnetic field with the magnetometer, building a detailed gravitational map of its interior mass, distribution with the radio science investigation, would not tell us everything about Earth's core. but it would tell us things we cannot learn any other way. It would give scientists a real, close-range measurement of the composition of a differentiated metallic body, something to test the models against, something to anchor the theoretical frameworks for planetary interior formation to actual observed reality rather than extrapolated inference. She proposed the mission to NASA in 2015. She was 50 years old. She had been studying planetary interiors for her entire career, and she was proposing a mission that, if selected, would take more than a decade from proposal to arrival. She would be 63 years old when the spacecraft reached the asteroid, if everything went according to schedule. That is what scientific ambition looks like at the scale of planetary exploration. Not a project you finish next year, not a paper you submit next month, a commitment that spans a significant fraction of a career, requiring faith that the funding will continue, that the hardware will work, that the launch vehicle will function, that 14 years of planning and building and waiting will ultimately place a machine in orbit around something that, right now, is just a cluster of radar reflections and spectral measurements interpreted from hundreds of millions of miles away. NASA selected the Psyche mission for development in January 2017. It was one of 2 missions selected in that round, the other being the Lucy mission to the Trojan asteroids that share Jupiter's orbit. Development proceeded through years of engineering work. A software issue in 2022 delayed the launch by a year, requiring a new trajectory to be calculated that used the Mars Gravity Assist instead of a direct path to the asteroid belt. The delay was costly and frustrating, but the new trajectory offered the calibration opportunities at Mars that the team has been using in May 2026 to their full advantage. Sometimes the detour is better than the original plan. The spacecraft launched on October 13, 2023. Elkins-Tanton was at Kennedy Space Center to watch the Falcon Heavy carry her mission into orbit. After 8 years of working toward this moment, the machine she had helped conceive and argue for and fight for and refine through countless reviews and budget cycles and technical challenges was finally in space. The mission carries 4 science instruments. The multispectral imager is the mission's eyes. It captures images in multiple wavelengths of light simultaneously, from visible to near infrared. By mapping how Psyche's surface reflects across the full spectral range, the team can build a composition map. Not just is the surface metallic, but which metals, in what mixture, distributed in what pattern. The spatial resolution from low orbit will allow scientists to see features the size of a tennis court from 50 miles altitude. The magnetometer is looking for something specific and telling. When iron cools below a temperature called the Curie point, approximately 1,418 degrees Fahrenheit for pure iron, the magnetic domains within the iron crystals can lock into alignment with whatever ambient magnetic field is present at the moment of cooling. The iron essentially freezes a record of the magnetic field into its crystal structure. If Psyche once had an active core dynamo, a churning liquid iron interior generating a magnetic field the way Earth's outer core generates one today, then the iron that solidified as the core cooled would have locked in a record of that ancient field. Remnant magnetism, fossil magnetism, a signature in the rock that persists for billions of years. If the magnetometer detects regions of remnant magnetism, that is strong evidence the asteroid once had an active magnetic dynamo, which would confirm it once had a liquid iron interior, which would be strong evidence it once had the layered structure of a differentiated body, exactly what the core remnant hypothesis predicts. If the magnetometer finds no remnant magnetism at all, that tells a different and equally interesting story. Either the asteroid never had a dynamo, suggesting it was never fully differentiated, or the material has been reheated and demagnetized by subsequent impacts. The gamma ray and neutron spectrometer measures elemental composition directly. When cosmic rays strike the surface of a rocky or metallic body, they interact with the nuclei of atoms in the surface material, producing secondary radiation at energies characteristic of the specific elements involved. Iron produces a specific gamma ray signature. Nickel produces a different one. Silicon, magnesium, sulfur, oxygen. Each element has a fingerprint in the gamma ray spectrum. By measuring this radiation from orbit, the spectrometer can determine what elements are present in the top meter or so of Psyche's surface and in what relative abundances. Not just is it metallic, but how much iron versus how much nickel. Whether there is sulfur indicating iron sulfide rather than pure iron metal. Whether there is significant silicon indicating silicate minerals mixed into the surface. The radio science investigation uses the spacecraft's own communication system as a science instrument. By tracking the Doppler shift of radio signals exchanged with the deep space network antennas on Earth, mission navigators can determine the spacecraft's velocity to extraordinary precision. By tracking how that velocity changes as the spacecraft moves through different regions of Psyche's gravitational field, scientists can map the gravitational field and infer how mass is distributed inside the asteroid. It is X-ray vision of a kind, using gravity to see what light cannot reach. 4 instruments, 4 different physical phenomena, 4 independent lines of evidence bearing on the same set of questions. What are you made of? How did you form? Did you once have a magnetic dynamo? How is your mass distributed? Are you what we think you are? Elkins-Tanton described the Mars flyby opportunity with a particular directness that cuts through all the technical complexity to the essential point. Ultimately, she said, the only reason for this flyby is to get a little help from Mars to speed us up and tilt our trajectory in the direction of the asteroid Psyche. But if all our instruments are powered up, and we can do important testing and calibration of the science instruments, that would be the icing on the cake. The icing on the cake. The gravity assist was the point. The calibration, the thousands of Mars observations, the satellite search rehearsal, all of that was the icing. The destination is Psyche. It has always been Psyche. And then there is NASA's own framing of what this mission means, stated in its mission documentation, with a plainness that makes the scale of it land harder than any elaborate description could. The Psyche spacecraft's voyage to its namesake asteroid could almost be considered a journey to the center of the Earth. Sit with that for a moment. Not a journey outward, a journey inward. Outward in the physical sense, yes, 2.2 billion miles into the asteroid belt, years of transit, borrowed gravity, and patient ion thrusters. But the destination, if the hypothesis is correct, is made of the same material that has been at the center of your planet since before your planet had a name. The iron core of the Earth has been there for approximately 4.5 billion years. It formed as the young Earth differentiated, the heavy iron and nickel sinking toward the center under gravity as the planet's interior melted. It has been there through the formation of the moon, through the emergence of life in the oceans, through every extinction event and every evolutionary radiation, through the entire history of everything that has ever lived or thought or built or wondered on this planet's surface. We have never touched it. We have never seen a sample of it. The core remains sealed, inaccessible. This is known only through the indirect evidence of seismic waves and the inferences of models, and we are sending a machine 2.2 billion miles into the asteroid belt to look at something that might be made of the same stuff, not a perfect analog, not a substitute for the measurements we cannot make directly, but the closest thing available, the closest thing that orbits our sun. The iron heart that has been beating 3,088 miles beneath your feet. Your entire life is, in a very real sense, what this mission is about. Not the journey outward to something alien and remote and disconnected from daily human experience. The journey outward to look at something that is as close to us, in the deepest sense, as anything in the solar system could be. That is why Lindy Elkins-Tanton spent 14 years working toward a moment when an instrument she helped design will finally see the surface of a world she has been studying from hundreds of millions of miles away. We are not going outward to look at something foreign. We are going outward to look at something that has been at the center of our world since before our world had a name. On May 17, 2026, 2 days after the Mars flyby, the Psyche mission entered a phase its planning documents call Cruise 2. It is, on paper, a straightforward label for a straightforward concept. The spacecraft is cruising. It is in transit. It has left Mars behind, and it is heading for the asteroid belt. Simple enough. But Cruise 2 will last 29 months. 29 months of continuous thrust. 29 months of the ion thrusters firing with almost no interruption. Building velocity with the patience of something that does not get tired, does not need sleep, does not require food or water or oxygen or company, just xenon gas and solar power and the cold mathematics of orbital mechanics, accumulating speed one small increment at a time across a void that has no landmarks and no edges and no milestones you can point to and say, "We are here, we have come this far, this much remains." Deep space does not offer those landmarks. There are stars in every direction, and they do not get noticeably closer or farther as you move. The asteroid belt, when the spacecraft enters it, will not announce itself. There is no boundary marker, no change in the texture of the dark. Just, eventually, the gradual statistical increase in the number of small bodies in the region, and among them, one specific body growing slowly from a point of light to a disk to something with features. That moment is still 29 months away from the Mars flyby. To understand why 29 months of continuous thrust is not only acceptable but necessary, it helps to understand how the spacecraft's propulsion system actually works, at a level of detail that goes a step deeper than the battery dropping analogy. The Psyche spacecraft carries approximately 2,030 pounds of xenon propellant at launch. Xenon is the heaviest of the stable noble gases, chosen for ion propulsion because it is chemically inert, dense enough to be stored compactly as a liquid, and its atoms are heavy enough to carry significant momentum when accelerated. The 4 thrusters on Psyche are called Hall effect thrusters, named after the Hall effect, a phenomenon in physics where a magnetic field applied perpendicular to an electric current causes charged particles to drift in a direction perpendicular to both. Edwin Hall discovered this effect in 1879 at Johns Hopkins University, using nothing more sophisticated than a gold foil, a battery, and a sensitive galvanometer. He was 24 years old. He had no idea that the effect bearing his name would eventually propel spacecraft to the asteroid belt. In a Hall effect thruster, xenon gas is fed into a cylindrical channel. A strong magnetic field is applied radially across the channel. Electrons injected into the channel are trapped by the magnetic field, forced to spiral around the field lines rather than flying straight through. These trapped electrons collide with the incoming xenon atoms, stripping electrons from the xenon atoms and converting them into positively charged xenon ions. An electric field applied along the axis of the channel then accelerates those xenon ions out of the thruster at roughly 24 miles per second, about 86,000 miles per hour, many times faster than the exhaust velocity of chemical rockets. 250 millinewtons per thruster, 4 thrusters. At maximum output with all 4 running, 1 newton of combined thrust. 1 newton is the force required to accelerate 1 kilogram of mass at 1 meter per second per second. It is roughly equivalent to the weight of an apple held in your hand. Applied to a spacecraft that weighs several tons, it produces an initial acceleration of approximately 0.2 millimeters per second. Every second the thrusters run, the spacecraft accelerates by 0.02 of a millimeter per second. In a minute, 1.2 millimeters per second. In an hour, roughly 0.16 miles per hour. In a day, about 3.8 miles per hour. In a month, roughly 115 miles per hour of additional velocity. In 29 months, something in the neighborhood of 3,300 miles per hour of accumulated velocity, added on top of whatever speed the spacecraft already had from the launch vehicle, the Mars Gravity Assist, and the first 18 months of ion thrusting before the flyby. It works because space has no air resistance. On Earth, the moment you stop applying force to a moving object, friction and air resistance slow it down. In the vacuum between Mars and the asteroid belt, a spacecraft pushed by 1 newton of force for 29 consecutive months accumulates that force as velocity, and that velocity does not go away when the thrusters stop. It stays. It compounds. Over a long enough timeline, continuous tiny force becomes significant speed. That is the logic of the ion thruster, not to compete with chemical rockets in the short term, but to win a race that runs across years and billions of miles. This kind of propulsion did not arrive fully formed. It has a history. Ion propulsion was theorized in the early days of spaceflight. Konstantin Tsiolkovsky proposed the concept of using electrically accelerated particles for propulsion in 1911. Hermann Oberth elaborated on the idea in the 1920s. For decades, it remained theoretical. The first operational test in space was NASA's Space Electric Rocket Test Mission in 1964, a simple demonstration that the technology worked in the actual space environment. The breakthrough demonstration came with Deep Space One, launched in 1998, which used a solar-powered ion drive as its primary propulsion system on a trajectory past an asteroid and then a comet. It worked, proving the concept operationally and giving mission designers the confidence to propose ion propulsion for future science missions. That confidence produced the Dawn mission, launched in 2007, and the direct technological ancestor of Psyche's propulsion system. Dawn orbited Vesta, left Vesta, and traveled across the belt to Ceres, something no chemical rocket mission could have done. Dawn demonstrated definitively that ion propulsion could carry a spacecraft across the asteroid belt, insert it into orbit around a target, and then leave that orbit and travel to a second target. Psyche's thrusters are a refined descendant of Dawn's, more efficient and more reliable, developed through the additional years of engineering work that followed Dawn's demonstration. A spacecraft with continuously running ion thrusters is not following a fixed orbit. It is continuously reshaping its orbit, bending it, adjusting it, fine-tuning the trajectory over weeks and months to hit an arrival target with extraordinary precision. The mission navigators at JPL run trajectory correction maneuvers on a regular schedule throughout the cruise phase, keeping the spacecraft on the precise path needed to arrive at the asteroid at the correct speed and angle for orbital insertion. The precision required is extraordinary. The spacecraft needs to arrive at asteroid Psyche not just anywhere near the asteroid, but at a specific approach direction and velocity that allows it to be captured into orbit efficiently. Hitting the required approach corridor from a distance of 280 million miles after traveling 2.2 billion miles over 6 years is comparable in geometric terms to throwing a ball from New York and having it pass through a window in Los Angeles without bouncing off the frame. Except the ball has been in flight for 6 years and the window has been moving the entire time. The Psyche spacecraft is not alone during this transit, in the sense that matters operationally. The Deep Space Network, operated by JPL, consists of 3 ground station complexes located at roughly 120-degree intervals around the globe: Goldstone in California, Madrid in Spain, and Canberra in Australia. The spacing ensures that as Earth rotates, at least one complex always has line of sight to any spacecraft in the solar system. The antennas at these complexes range from 26 meters to 70 meters in diameter, the largest being the 70-meter dish at Goldstone. They need to be large because the signals from deep space spacecraft are extraordinarily faint. By the time a radio signal from Psyche travels hundreds of millions of miles and reaches Earth, its power is measured in fractions of a trillionth of a watt. During Cruise 2, the Psyche spacecraft transmits engineering data back to Earth daily, reporting on the health of each subsystem: thruster performance, solar array power output, propellant levels, temperature readings, the status of each instrument. The mission team at JPL reviews this telemetry on a regular schedule, looking for any anomalies that might indicate a developing problem. Most of the time, nothing happens. The thrusters fire, the solar arrays track the sun. The telemetry reports nominal across every channel. This is what most of a deep space mission looks like, not the dramatic launches and the tense orbital insertions that make the news. The long quiet middle, the cruise. This is the patient waiting while the spacecraft travels distances that no human intuition is equipped to properly visualize. Tonight, as you settle into sleep, the Psyche spacecraft is somewhere in that long dark between Mars and the asteroid belt. The main body of the spacecraft, the bus, is approximately 6.5 feet long and about 4 feet wide. The solar arrays, which must collect enough sunlight to power the ion thrusters at the asteroid belt's greater distance from the Sun, extend to a total span of approximately 75 feet when fully deployed, wider than the wingspan of some commercial aircraft. The spacecraft is a machine that is mostly wings, solar wings, with a small central body carrying the fuel and the instruments and the computers. From any distance that means anything in the context of the solar system, it is invisible. It is a small machine in a very large place, following a path calculated years in advance by engineers who will never ride along, executing commands loaded into its flight computer by a team who communicate with it at the speed of light across a distance that means even those communications arrive minutes after they were sent. The blue glow of the ion thrusters is real. It is not an artistic embellishment. When xenon ions are accelerated through the Hall effect thruster and expelled from the nozzle at 86,000 miles per hour, they carry enough kinetic energy to emit light in the blue-violet part of the visible spectrum. If you could somehow float alongside the Psyche spacecraft in the dark right now, close enough to see it, you would see that glow. A pale, quiet, steady blue-violet light at the rear of the machine, barely bright enough to be called light at all against the surrounding dark, pushing the spacecraft forward with less force than the weight of a piece of fruit, with the patience of something that has nowhere else to be and nothing else to do. The asteroid belt lies ahead, not the dense, dramatic asteroid belt of science fiction, full of tumbling rocks, threatening to collide with anything that passes through. The real asteroid belt is almost entirely empty space. The probability of a spacecraft colliding with an asteroid while crossing the belt is extremely low. The belt simply does not contain enough material per unit volume to make collisions likely. But it does contain asteroid Psyche, 173 miles wide, rotating every 4 hours and 12 minutes, made in all probability of iron and nickel, ancient beyond any human framework for understanding age, patient beyond any comparison, arriving July 2029, 3 years and 2 months from tonight. And when the spacecraft arrives, everything changes. The long cruise ends, the science begins. The questions that Lindy Elkins-Tanton has spent her career asking will finally have access to the answers, but that is still 29 months away. For now, there is just the dark, and the blue glow, and the patient, continuous arithmetic of 1 Newton pushing a van-sized machine through the emptiness, adding velocity in increments too small to feel, across distances too large to see. So why does this change how we think about space travel? That was the second half of the title's promise. We have covered the how, the gravity assist mechanics, the ion thrusters, the flyby geometry, the 2,800 miles above Mars at 12,333 miles per hour, the calibration campaign, the satellite search rehearsal, the 29 months of continuous thrust still ahead, the what and the when and the where. But the why, the reason this answer changes something rather than just explaining something, is a different kind of question, and it deserves a slower kind of answer, because the change is not technical. The change is perceptual. It is a change in how you see the solar system itself, and that kind of change, once it happens, does not unhappen. Most of us, when we picture a spacecraft traveling through space, picture something like a ship crossing an ocean. The ship has a destination. It uses its engines to cross the water between here and there. The ocean is the medium. It is what the ship must pass through to get somewhere. The ocean is essentially passive, a thing to be crossed rather than a thing to be used. The ship's power comes from within itself, and the ocean mostly cooperates with this framing. Yes, there are currents. The trade winds that powered centuries of global exploration were understood and exploited long before anyone understood the atmospheric dynamics that created them. The Gulf Stream was charted by Benjamin Franklin in the 18th century because sailors on mail ships had noticed that westward crossings of the Atlantic took longer than eastward ones, and Franklin wanted to know why. But even accounting for currents and winds, the ocean analogy for space travel gets something fundamentally wrong. The ocean is two-dimensional, or close enough. You navigate across a surface, and the ocean does not move. It stays put while the ship crosses it. The solar system is none of those things. The solar system is three-dimensional in a way that matters for navigation. Every planet orbits in a slightly different plane, slightly inclined relative to every other. So reaching different targets requires not just traveling the right distance, but changing the plane of your orbit, which requires energy, which requires either fuel or a gravity assist from a body that happens to be moving in the right plane at the right time. The solar system is not passive. Every object in it is moving continuously at speeds that dwarf anything achievable by chemical rockets. Mars moves at 54,000 miles per hour. Jupiter moves at 29,000 miles per hour. The momentum locked into these orbital velocities is so large that even a tiny fraction of it, borrowed by a spacecraft during a flyby, can transform a mission from impossible to achievable. And the solar system moves, all of it. The Sun itself is moving through the Milky Way at about 450,000 miles per hour, carrying the entire solar system with it. The destinations are not sitting still, waiting to be reached. They are moving targets, continuously changing their positions relative to each other. And the art of deep space navigation is the art of predicting where they will be and arranging to meet them there. Engineers who navigate spacecraft through the solar system are not crossing a passive medium. They are reading a dynamic landscape, a landscape made entirely of invisible force and continuous motion that can be used or wasted depending entirely on how well you understand its geometry. That geometry has a formal name in orbital mechanics. It is called the solution space, and it refers to the full set of possible trajectories that could take a spacecraft from its origin to its destination within a given set of constraints. Time of flight, fuel consumption, arrival velocity, trajectory geometry relative to the target, all of these are variables, and they interact with each other in ways that are not intuitive. The planetary alignment that makes a particular gravity assist possible exists for a limited window. Miss the window, and you must either wait years for the geometry to recur, use more fuel to compensate, or accept a longer flight time. The trajectory designers who found the solution for the Psyche mission were solving an optimization problem in a solution space with millions of possible trajectories, looking for the combination of launch date, flyby parameters, and arrival conditions that satisfied all the mission requirements simultaneously. The engineers who do this work are, in a very real sense, cartographers. They are mapping invisible terrain, the gravitational landscape of the solar system, and finding the paths through it that are most efficient, most elegant, most aligned with the mission's objectives. They are reading something that has been there all along. The Voyager mission surfed it. A once in 176 years alignment of the outer planets created a sequence of gravitational currents that no mission planner in 1977 had any reasonable hope of seeing again in their professional lifetime. The window was real, the physics were clear, and a team at JPL that included a young trajectory analyst named Gary Flandreau, who had identified the alignment in 1965 while working as a summer intern, spent years arguing that this opportunity must not be missed. It was not missed. Voyager 2 used Jupiter to reach Saturn, Saturn to reach Uranus, Uranus to reach Neptune. 4 planetary encounters, each one using the gravity of a world to add velocity and reshape the trajectory for the next. Without those assists, reaching Neptune would have required 30 years. With them, Voyager 2 arrived in 12. Today, Voyager 1 is more than 15 billion miles from the Sun. It crossed the heliopause in 2012, becoming the first human-made object to enter interstellar space. It is still transmitting. The signal, traveling at the speed of light, takes more than 22 hours to reach Earth. A spacecraft launched in 1977, powered by borrowed gravity, still doing science 49 years later. Cassini surfed it. 4 planetary flybys, Venus twice, Earth once, Jupiter once, each one adding velocity and reshaping the trajectory, spending nothing from the spacecraft's propellant budget that could not be better spent on the orbital science campaign at Saturn. Europa Clipper is surfing it right now. Launched in October 2024 and designed to study Jupiter's moon Europa in unprecedented detail, Europa Clipper used a Mars flyby in March 2025 and will use an Earth flyby in December 2026 to build the velocity it needs before swinging past Jupiter and entering its system in 2030. Europa is one of the most compelling targets in the solar system for astrobiology. Beneath its icy surface, scientists believe, lies a global ocean of liquid water, kept from freezing by tidal heating generated by Jupiter's immense gravitational pull. The ocean has probably existed for the age of the solar system. It is in contact with a rocky seafloor. The ingredients for life as we understand it are plausible in that environment. If we find evidence of life anywhere in the solar system beyond Earth, Europa is one of the places scientists most frequently point to when asked where they would look first. And getting there required Mars. Think about what this means for the deeper future. Any mission to the moons of Saturn, Enceladus, with its subsurface ocean and plumes of water vapor, Titan with its methane seas and complex organic chemistry, will require the same strategy Europa Clipper is using now. This will require multiple flybys, borrowed momentum, and years of patient transit. Any mission to Uranus or Neptune will require a launch window timed to Jupiter's position. Jupiter is the most massive planet, the greatest gravitational engine in the solar system, and getting to the ice giants efficiently requires borrowing from Jupiter's immense orbital momentum. The launch windows that provide Jupiter assists to Uranus and Neptune occur only every 10 to 15 years. Missing one means waiting more than a decade. And beyond the planets, in the truly distant future, any mission to another star system will face the most extreme version of this challenge. The nearest star system to Earth, Alpha Centauri, is approximately 4.37 light-years away. At the speed of Voyager 1, the fastest human-made object ever launched, and one that reached that speed partly through gravity assists at Jupiter and Saturn, the journey would take approximately 73,000 years. No plausible propulsion technology currently envisioned can close that gap to a human lifetime. But theoretical mission designs for interstellar probes have explored using the Sun itself as a gravitational engine. A spacecraft could dive extremely close to the Sun, using the Sun's immense gravity to bend its trajectory into an extremely tight arc, then fire a powerful burst of thrust at the closest approach point, the perihelion, where the spacecraft is moving fastest. The combination of the perihelion velocity from falling toward the Sun and the additional thrust at that optimal moment could produce an exit velocity far exceeding anything achievable by burning fuel alone at a comfortable distance. This is called an Oberth maneuver, named for Hermann Oberth, who first described the physics. The interstellar probe concept, developed by Johns Hopkins Applied Physics Laboratory, uses a solar gravity assist as its primary velocity building mechanism, diving inside the orbit of Mercury to maximize the gravitational energy extracted before heading outward into the deep dark beyond the heliosphere. That mission, if it is ever built, will be the direct philosophical descendant of Mariner 10, using Venus, of Voyager using 4 planets in sequence, of Cassini and Europa Clipper and Psyche. It is the same insight, carried forward across generations of spacecraft and mission designers. The solar system is not an empty road to be driven across. It is a machine full of energy and momentum, and that energy and momentum belong to anyone patient enough to read the geometry and brave enough to use it. There is something quietly beautiful in that, if you let yourself sit with it long enough. We tend to think of space exploration as a triumph of engineering. Engines and materials and computers and communication systems, human ingenuity built into hardware, launched into the void. And it is all of those things. But the gravity assist is something different from engineering. You cannot engineer a better gravity assist. You cannot upgrade it or manufacture it or improve its specifications. It is not a technology. It is a discovery. The recognition that something has always been there, that the solar system has always been full of orbital momentum, that planets have always been moving at tens of thousands of miles per hour and pulling on everything around them, and that a spacecraft in the right place at the right time can borrow from that motion without cost, without loss to the planet, and with transformational benefit to the mission. Gary Flandreau identified the Grand Tour alignment in 1965 while sitting at a desk at JPL with paper and pencil, calculating where the outer planets would be a decade hence, noticing that the geometry would allow what had never been attempted. He was reading something the solar system had been offering for billions of years and would offer again in 176 years, whether anyone noticed or not. The momentum was always there. The opportunity was always there. The solar system was always a machine that would carry things to the outer planets if those things arrived at the right place at the right time, moving in the right direction. All that was required was someone paying close enough attention to notice. That is not engineering, that is navigation. And navigation of this kind, reading an invisible landscape and finding the path through it, is something humanity is only beginning to fully understand after 6 decades of deep space exploration. We are, in a very real sense, still learning to read the solar system. The lines are beautiful, not because they were designed to be beautiful, because the mathematics of the solar system is beautiful in the way that all deep structure is beautiful when you finally see it clearly. The planets move in ellipses because gravity falls off with the square of the distance. The gravity assists work because momentum is conserved. The trajectories bend in precisely the ways they bend because the universe has rules, and the rules are consistent, and the consistency means that if you understand them well enough, you can predict where everything will be and use that knowledge to go places that would otherwise be unreachable. The spacecraft currently trailing a faint blue glow through the dark between Mars and the asteroid belt is there because, a long time ago, people started paying attention. And because they kept paying attention, generation after generation of mission designers and trajectory analysts and engineers and scientists, each one building on what the previous ones learned, each one reading a little more of the invisible landscape, each one sending machines a little farther and with a little more precision than what came before. And tonight, while you drift towards sleep, all of it is still happening. Mars is in its orbit, moving at 54,000 miles per hour, completely indifferent to the spacecraft that recently borrowed a fraction of its momentum and slipped away into the dark. The Psyche spacecraft is in cruise 2, thrusters firing, the faint blue glow steady and continuous, building velocity 1 ion at a time across a gap of hundreds of millions of miles. Jupiter is where it always is, the great gravitational engine of the solar system, pulling on everything around it with quiet, massive force, available to any mission that can reach it at the right time on the right trajectory. And somewhere in the asteroid belt, a metallic world 173 miles wide is completing another slow orbit around the Sun, as it has for 4.5 billion years, as it will continue to do, patient and indifferent, until the moment in July 2029 when a machine made of aluminum and titanium and human ambition falls into orbit around it and begins to ask it questions. What answers come back from that world will tell us something about the early solar system, something about how planets build their cores, something about the iron heart that has been 4,000 miles beneath your feet your entire life, beating in the dark, holding the magnetic field that keeps the atmosphere in place, doing the quiet work that makes this planet livable, sent back across 2.2 billion miles on a signal traveling at the speed of light, taking 25 minutes to arrive, landing on a screen in Pasadena, California, where someone will be sitting very still, reading very carefully, asking the oldest question in science. What does this mean? Thank you for spending your night drifting through the cosmos with Cosmic Drift. This is what we do here. Not the highlights and the countdowns and the breathless announcements, the slow version. The version with the physics explained carefully, and the history traced all the way back, and the human story told with the patience it deserves. If that is the kind of science storytelling you want to fall asleep to, you know where to find us. Subscribe if you have not already. Every video is built the same way. Real missions, real scientists, real numbers, and all the time in the world. Tonight's journey is over. The spacecraft's is not. We began tonight with a question. Why did NASA use Mars to reach an asteroid? It is a question that sounds simple. It has a simple version of an answer: the gravity assist, borrowed momentum, the physics of orbital mechanics. You could give that simple answer in 3 sentences, and it would be true. It would be factually accurate. It would not be wrong. But we did not come here tonight for the simple version. We came here to understand it. And there is a difference between knowing an answer and understanding it. The same difference there is between being told that the Earth has an iron core and spending a quiet hour with the evidence for why that is almost certainly true, and what it means that we will never directly see it. The simple version of this answer is a fact. What we have been building together for the last 2.5 hours is something else, a way of seeing. Let's close with what changed. Before tonight, if someone had asked you how spacecraft travel through the solar system, you probably would have said something about engines and fuel and pointing in the right direction. You would have been describing something real. Chemical rockets do use engines. They do burn fuel. They do point. But the picture would have been missing something. The solar system in that picture is passive, empty, a void to be crossed. The spacecraft provides all the energy. The space provides none. After tonight, the picture is different. The solar system in the new picture is active, full. Every planet moving at tens of thousands of miles per hour, carrying momentum that has been accumulating since the formation of the solar system, available to any spacecraft that arrives in the right place at the right time, moving in the right direction. The space between the planets is not empty in any meaningful sense. It is structured, shaped by the overlapping gravitational fields of everything in it, threaded with invisible currents of momentum that engineers have been learning to read and use for 50 years. The spacecraft in the new picture is not just an engine. It is a surfer. It is something that moves through a dynamic medium by reading that medium and using what it offers rather than fighting what it is. That shift is what this video's title was pointing at. Not just why NASA used Mars, but why the answer changes something. And it does change something, even if the change is quiet. Even if it is the kind of change that you will only notice later, when you read about a future mission's trajectory and find yourself thinking about which planet it is going to use, and why, and whether the geometry will work. Now, that honest answer we promised. NASA did not use Mars. Mars has no awareness of what happened on May 15, 2026. It registered no event. Nothing about it changed. Its orbit did not shift. Its rotation did not alter. Its surface, already ancient and weathered and silent, recorded nothing. The Olympus Mons volcano, the largest in the solar system, sat exactly where it has sat for billions of years. Valles Marineris, 2,500 miles long, and in places 4 miles deep, continued to lie along the equatorial region unchanged. The thin atmosphere continued its slow circulation. Dust particles suspended in the carbon dioxide, catching the sunlight in the way they have caught it since long before any life on Earth had eyes to notice. Mars did not participate in the gravity assist. It did not offer anything. It did not consent to it or facilitate it or cooperate with it in any way. It simply continued doing what it has been doing for 4.5 billion years, which is orbit the Sun at a fixed average speed along a path determined by the gravitational relationship between Mars and the Sun that has existed since the solar system's formation. NASA did not use Mars. NASA calculated where Mars would be. The calculation began years before the May 2026 flyby. Trajectory designers at JPL worked through the orbital mechanics, finding the solution that satisfied all the mission requirements. They determined that a spacecraft launched on October 13, 2023, following a specific path through the inner solar system, would arrive at a specific point in space at a specific time that would place it in exactly the right geometric relationship with Mars for the gravity assist to work. Then they built the spacecraft. Then they launched it. Then they monitored its trajectory for 2.5 years, making small corrections along the way to keep it on the calculated path. And on May 15, 2026, the spacecraft was where the calculation said it would be, and Mars was where the orbital mechanics said it would be, and the laws of physics that operate at every scale in the universe did what they always do. Mars pulled, the spacecraft curved, the spacecraft left. Mars continued. That is what it means to use the solar system as a propulsion system. Not to command the planets, not to enlist them or recruit them or direct them, but to understand them well enough to place a machine in the exact right position at the exact right moment, and let the physics do what the physics was going to do anyway. The gravity was always there. The orbital momentum was always there. Mars was always going to be where it was on May 15, 2026. Following the orbit it has followed for 4.5 billion years, carrying the momentum it has carried since the solar system formed. All that was required was knowing that and being patient enough to use it. There is a quality to that patience that feels worth naming before we close. The Psyche mission began in earnest with Lindy Elkins-Tanton's proposal to NASA in 2015. The spacecraft will arrive at the asteroid in July 2029, 14 years from proposal to arrival, 14 years of sustained effort by hundreds of people. This has spanned funding cycles and review boards and technical challenges, and a launch delay and a trajectory redesign, and 2.5 years of deep space transit, and 29 more months of Cruise 2 still to go. The scientists who will analyze the first data from asteroid Psyche's surface have probably been thinking about this mission for a decade or more. Some of them were graduate students when the mission was proposed. Some of them are now the experienced researchers who will lead the analysis. Some of the graduate students who will be working on the data in 2029 have not yet started their doctorates. The mission will span careers. It already has. Deep space exploration requires this kind of patience. Not the patience of waiting passively for something to happen, but the patience of sustained attention over long timescales, of keeping a complex technical and scientific enterprise coherent and funded and focused across a span of time in which many things change. The patience required to do this work is not natural to human beings. We are built for timescales of days and seasons and years, not decades. We are built to want feedback, to want the story to resolve, to want to know what happened. Deep space exploration does not give you that on a human schedule. It gives you the data when the spacecraft arrives, not before. And the spacecraft arrives when the orbital mechanics say it arrives, not when you are ready. Learning to work within those constraints, to sustain the attention and the funding and the institutional commitment across timescales that exceed individual careers, is one of the less celebrated but most important things that space agencies have learned to do. It is a form of civilizational patience. the ability of a civilization to invest in questions whose answers will not arrive for a generation. It is the same patience that built the great cathedrals of medieval Europe, some of which took 200 years to complete and were begun by architects who knew they would never see the finished building. It is the same patience that drives the construction of giant telescopes that will be used by scientists not yet born. It is the same patience that sends a spacecraft to a metal asteroid in the asteroid belt and then waits 14 years for the data. That patience is worth something, not just for the science it enables, though the science matters enormously, but as an example of what a civilization is capable of when it decides that some questions are worth answering on any timescale, not just a convenient one. The spacecraft will arrive at asteroid Psyche in July 2029. When it does, it will spend approximately 3 weeks approaching the asteroid, its cameras imaging the surface at ever-increasing resolution, the science team getting their first real look at the world they have been thinking about for so long. The satellite search will be conducted in earnest, the same search rehearsed during the Mars flyby. The approach trajectory will be carefully monitored and adjusted. Then, when the team is confident about the local environment, the spacecraft will use its ion thrusters to slow down gradually and allow itself to be captured into orbit. Not a single burn the way a chemical rocket orbital insertion is. A gradual process, the continuous low thrust of the ion drive reshaping the trajectory over days until the spacecraft is in a stable orbit around the asteroid. And then the science begins. The multispectral imager will begin building its surface map. The magnetometer will start its search for remnant magnetic signatures. The gamma ray and neutron spectrometer will measure the elemental composition of the surface below. The radio science investigation will begin the long process of building the gravitational field map. The first results will not come all at once. The data will come in, it will be processed, it will be analyzed, it will be written up and reviewed and published. Questions will be answered, and new questions will be raised by the answers. The model of what Psyche is will be updated, refined, challenged, and revised as the data accumulates. That is how science works. Not a single revelation, but a long, careful, iterative process of measurement and interpretation and revision. Not the end of the story, but the beginning of a new chapter. And somewhere in that process, scientists will learn something new about how rocky planets build their cores, something that will make the models better, something that will change, in some small or possibly large way, the answer to the question of how the inner solar system came to be the way it is, including, perhaps, something about the iron heart of the planet you are lying on right now.